the first atmosphere on a rocky exoplanet in a habitable zone. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. For the first time, scientists have detected an atmosphere on a rocky world orbiting in the habitable zone of another star. This week I'm joined by the lead author on that discovery, Collin Cherubim, a NASA Hubble Fellow at the University of Chicago. Then Bruce Betts, our chief scientist, joins me for What's Up, where we're going to dig into the very first detection of an exoplanet atmosphere ever, and its surprising connection to this week's guest. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. One of the greatest questions humanity has ever asked is whether or not we're alone in the universe. Is there life beyond our planet? To truly get at the heart of that question, though, we need to understand the conditions under which life arose on our own planet, and then search for those conditions elsewhere among the stars. It's true that there could be other circumstances under which life can thrive, perhaps in the subsurface liquid water oceans of an exomoon, or maybe in situations that we haven't even fathomed. But for now, we only have one example of a world that's teeming with life: our Earth. If we could find a similar world out there in the vastness beyond our solar system, it would be extraordinary. As of the date of this recording, humanity has confirmed 6,333 exoplanets, worlds orbiting stars beyond our solar system. And there are thousands more candidates waiting for follow-up observations. But the vast majority of these worlds are nothing like Earth. We've found hot Jupiters, mini Neptunes, lava worlds, rogue planets, endless permutations of possibilities out there orbiting other stars. But a world like our own? That's something that we've yet to see. The search is still ongoing, but it took a major leap forward with the world that we're about to discuss today. The exoplanet is called LHS 1140b. It's a super-Earth, about 1.5 times the size of our planet and roughly 5.5 times its mass. It orbits a small, cool red dwarf star about 49 light-years away in the constellation Cetus. It's not only a rocky world, but it orbits in its star's habitable zone, just the right distance that liquid water could conceivably exist on its surface. We don't yet know whether or not it has an ocean, but each new piece of evidence makes this world more and more intriguing. And now we know something else. It actually has an atmosphere, a layer of gas shrouding it that can insulate and protect its surface. When researchers observed LHS 1140b, they didn't find an atmosphere that's like Earth's, but they did find an atmosphere of helium, the second most abundant element in the universe. As our guest is going to explain, that helium can tell us a great deal, not only about this world, but perhaps about the evolution of rocky worlds with atmospheres. To walk us through how this discovery happened and what it means, I'm joined by the lead author on this paper, Dr. Collin Cherubim. He's a NASA Hubble Fellow at the University of Chicago who recently completed his PhD at Harvard. His team's paper is called Helium Escaping from the Atmosphere of a Nearby Rocky Exoplanet Orbiting in a Habitable Zone, and it was published in the journal Science on July 16th, 2026. Hey, Collin, thanks for joining me.
Hey, Sarah, thanks for having me here.
And congratulations on your PhD. I understand that just happened recently.
Yeah, thanks so much. Yeah, I just finished up at Harvard University in the Earth and Planetary Science Department in May.
So you've had one of the most unusual paths in astrophysics that I've kind of come across as I've been interviewing people, right? You got a chemistry degree, you were a professional drummer, a high school teacher, and then off to get all of this science, all this background in exploring worlds. How did that long, winding road lead you to hunting atmospheres on other worlds?
Yeah, I suppose it was a bit unusual. The truth is, one day I went to my gym in Boston when I was a high school teacher, and the guy working behind the counter said, "Hey, what's your favorite element?" I said, "What?" And I kind of did a double take, like, is he talking to me? And I was like, chemical element? He said, yeah. I said, well, it's funny you ask because I'm a chemistry teacher. And so I told him it was carbon, which I know some people will think is a cop out, but I mean, you can't really beat carbon. And I said, why? And he said, oh, I'm just reading this book. I was just curious. And I said, okay, what's the book? And it was Cosmos by Carl Sagan. And I was aware of the reboot by Neil deGrasse Tyson, the TV show, and sort of aware of the book and Carl Sagan, but I didn't really know much about it. And it looked interesting. So I picked it up and I read it, and it sounds cliche, but it changed my life. And I was really, really inspired. And it kind of snowballed into what started as more like pop sci, Neil deGrasse Tyson and Carl Sagan and folks like that, and podcasts and things. And then I just became more and more curious and thought like, hey, maybe I can actually engage with this kind of academically. And so I started trying to read academic literature and sort of cold emailing grad students and professors and just asking questions. And eventually, I was kind of looking for something more intellectually and always wanted to do science. And I thought, hey, maybe I can actually, try to go get a PhD in this. And so I did a lot of like online courses to try to, get a better foundation in like computer science and physics and things like that. And I took a job teaching physics very intentionally to try to strengthen that background, and applied to a bunch of programs and didn't get into any of them, and took some feedback and got some experience, and then reapplied and then got into Harvard.
I think it's really interesting just how many people Carl Sagan inspired. I mean, honestly, he was a huge part of my journey because Cosmos was something that inspired me when I was a kid. And now here I am working at the organization that he co-founded, right? I can't even put to words how many people's lives have been completely changed by that. And I wish we could tell him,
Yeah, it's a shame we can't. I think he would be really, moved by some of the things that we see today. I recently went back and just read that book again towards the end of my PhD, and it was a completely different experience because, I'm reading through it, I'm thinking, oh, well, actually, that's not quite right. And, oh man, if only he could know, how many planets are, discovered today, et cetera, et cetera. So yeah, things, especially in exoplanet science, things have changed so much. Yeah.
I mean, they really, really have. And I think, this paper is a really great example of this because one of your PhD advisors, I think, is David Charbonneau. Is that right?
That's right.
Yeah. So he was part of the team that made the very first detection of an atmosphere on an exoplanet. And that was back in 2001, right? So not that long ago. And of course, it was hot Jupiter, classic, right? But now 25 years later, you two are co-authors on the first atmosphere detected on a rocky planet in the habitable zone. I mean, that is a wild amount of progress in just 25 years or so. What was it like working with David on this?
Yeah, honestly, it was kind of surreal. I'm like almost speechless. It's really something to see sort of Dave's take on it too, and he has the experience, right? Like you said, he discovered the first ever transiting exoplanet, and then the first ever atmosphere on an exoplanet, known to us, of course. And I heard him reminiscing about at that time, I think he said he kind of speculated and thought, oh, maybe someday we can do this for, sort of an Earth-like, more rocky, smaller planet. But I think at that time it felt far-fetched to him, and it felt like maybe a bit of a pipe dream, or I hope I'm not getting him wrong. Maybe it was more of just an engineering challenge that he thought inevitably would be solved, or maybe it was all of these things. I don't know. But, the way he kind of reminisced about it, and then 25 years later, he's got a student that he's guided and helped along, and together here we are, having discovered that atmosphere that he kind of dreamt about in a way.
I think what's funny about this is, at least from my understanding of the arc of this story, you didn't originally go seeking to find an atmosphere on a, rocky world in the habitable zone, right? You were actually kind of interested in this kind of part of the arc of planetary evolution, that moment where the atmosphere is dominated by helium. Was that actually what you were trying to look for?
Yeah. The fact that it was a habitable zone planet was a total bonus. I was working on a lot of theory, not just observation, but theory work as a PhD student. And I developed a model that simulates how exoplanet atmospheres evolve over time. And I was specifically predicting helium-dominated atmospheres on a select number of planets. And LHS 1140b just sort of happened to be one of them. And I thought, well, hey, that's a really interesting target. You know, it's a rocky world in the habitable zone that has received tons of attention. It's nearby, so it's easy to observe. And I thought, well, why don't we just start here and test the theory with this really fascinating planet? And lo and behold, it was the first detection.
Can you talk a little bit about how these planets start out and why this moment when helium is dominating the atmosphere is so interesting?
So we think most planets, when they form in what's called a protoplanetary disk. And this is kind of the leftover gas and dust encircling a star when a star sort of collapses from a giant molecular cloud and it ignites fusion and such. And so you have this leftover disk circling the star, and slowly particles start to accumulate through gravity, and you build up these pebbles, and then the pebbles kind of coalesce and you get planets. And most material in the universe actually is hydrogen and helium. These are the most abundant elements in the universe. They were formed during the Big Bang. They're just the simplest elements, 1 proton, 2 protons. And there's just a lot of the stuff laying around in these disks. So we think most planets start with hydrogen and helium dominated atmospheres. We think the solar system might actually be a bit of an oddball, and that may not have happened, although recent theories are suggesting this actually may have happened to Earth, and Earth itself may actually have gone through one of these helium phases, which maybe we can dig into. But yeah, so we assume that these planets start with hydrogen and helium. And what my prediction focuses on is this kind of sweet spot where if a planet has the right mass, so the right gravitational strength, which wants to keep the atmosphere, and the right stellar irradiation, so heating from the star that wants to blow the atmosphere away. These are kind of competing forces. If you're in this sort of sweet spot, you can drive away the hydrogen, but the helium, which is heavier, can stick around and sort of accumulate on the planet. And this is called mass fractionation. And you sort of enrich the atmosphere in helium over time.
And it's like you're looking for this at least on cosmic timescales, a very small time window in the lives of these worlds, which is, it's got to be a real challenge. So out of all the worlds that you looked at, how many qualified for this moment? And why did you end up looking at LHS 1140b?
Well, they may not actually be too much of a transient state. They might not be that short time scale. At least my model simulations are suggesting that they should be stable for hundreds of millions of years, and in some cases billions of years. Yeah, that they can kind of have these helium dominated atmospheres. So, you can check out my 2025 paper, which was a theory paper coming from my latest modeling work. And there's a couple dozen planets in a table there that have, helium rich atmospheres predicted to exist on them with certain probabilities ascribed to them based on some simulations I've done. This idea of a helium dominated atmosphere was put forth formally in 2015. And I've kind of revised this hypothesis with more detailed modeling. And it was once kind of thought to be maybe a sort of exotic world, this sort of helium world scenario. But my thesis showed that it may actually be kind of a common process that is almost like a natural stepping stone for planets of this size as they cross over and start to, lose their atmospheres and they go from more gaseous planets to kind of more rocky planets. So yeah, in that respect, it kind of is maybe like a sort of stepping stone, but some of these planets can kind of stay in that transient state for hundreds of millions to billions of years. And in this case in particular, we think LHS 1140b, according to my simulations at least, should be stable in this state for at least, several hundreds of millions of years to come, if not over 1 billion years.
That's amazing.
Yeah.
You're saying basically there are certain conditions, both with the planet and with the star, under which this can happen. So can you tell us a little bit about the world and the star itself and how this scenario sets us up for success looking for helium?
So I think the main things to focus on are the mass of the planet and the distance to the star, which kind of tells you how irradiated the planet is. If the planet has the right escape velocity, or equivalently, you could think of it as like surface gravity, how strongly the planet wants to hold on to its atmosphere, and compare that to how irradiated the planet is from its star, those are kind of the two balancing forces that are going to tell you how likely it is for the planet to hold on to its atmosphere. And if it's tuned just in the right kind of parameter space on those two axes or two dimensions, and the balance is just right, you can blow off enough hydrogen that you remove most of it, but not too much that you're dragging helium along with it. I'm kind of getting at something called the cosmic shoreline here, which is this concept that was introduced in 2017, I think by Kevin Zanley and some folks, which is basically what I'm saying, but it's based on the solar system. So what they did is they just plotted graphed all of the solar system planets on those two axes. How strong is their gravity and how irradiated are they by the sun? And they found they could draw this really nice line through the planets such that the planets with atmospheres were on one side of the line and planets that don't have atmospheres were on the other side of the line. And they said, hey, maybe this is like a cool guiding principle that we can extrapolate to predict which exoplanets might have atmospheres and might not have atmospheres. What's really cool about this system, LHS 1140, is it has two rocky planets on either side of this cosmic shoreline. And just as the cosmic shoreline predicts, the smaller, hotter, closer in planet, LHS 1140c, does not have an atmosphere. And we now know LHS 1140b, the larger, colder one, farther out, does have an atmosphere. So it's kind of one awesome observational confirmation of that model.
Yeah, and you had the perfect occasion to see both of these worlds, and it was honestly really wonderful timing. So you not only looked at C, but you looked at B, and during a time when they were both going to be transiting their star within the space of a day. How did you determine the right moment to do that?
Yeah, I'd like to say it was the product of some romantic mathematical calculations that are on a chalkboard somewhere in my office, but there's a transit and ephemeris service. It's a computer program that NASA provides on the NASA Exoplanet Archive that's really helpful for planning observations. So yeah, I just used that, frankly, and they can, based on previous observations of the two planets, you can predict in the future when they should be crossing in front of their star or transiting so that you can observe them. And for LHS 1140b, the habitable zone planet, it's on a 25-day orbit. So its year is 25 days, which sounds really short. But because the star is just a fraction of the brightness of our sun, it actually receives slightly less radiation from its star than the Earth does from its sun. But that's still a very relatively long orbital period as far as exoplanets go. And what I'm getting at is that's actually pretty difficult to observe from the ground when you need it to be nighttime. And so that's pretty rare. You can really only observe this planet transit from the ground like one or two times. And then so for LHS 1140c, the closer in one, to be also transiting on the same night when the weather's good in the southern hemisphere and, separated by a couple of hours so they're not overlapping, so you can actually, see both separately, is extremely rare. And I'm not even sure it's going to happen again like this century, frankly.
What does that allow you to do that you can't do by looking at them on different nights? So
for one thing, it's just really efficient and a good use of the time on the telescope, which is very competitive, right? If you have an idea that you want to test using a telescope, you have to write up a formal proposal and submit it to a time allocation committee, and you're competing for this resource with many other people, and your idea has to be good to get selected. So for one thing, it's just a great science case. You get a lot of bang for your buck. I'm saying, hey, I just need one night and I can get 2 planets. How cool. And they happen to be really interesting planets. But scientifically, what else we can actually get from them transiting on the same night is, I'm going to try not to get too technical here, but there's something called the transit light source effect. And basically, that just means when a planet passes in front of the star from our vantage point on Earth, and we're looking for chemical signatures in the planet's atmosphere via spectroscopy, sometimes if the planet, let's say it's just a bare rock and it doesn't even have an atmosphere, if that planet passes in front of a spot on the star that happens to just have some sort of molecular absorption going on in it, it can mimic the signal of an atmosphere on the planet. And this is tough. This is a false positive, right? This is telling us like, oh, hey, it looks like there's an atmosphere on this planet, but really it's just the star. And what's nice about two planets transiting on the same night is because they have relatively similar, what we call transit chords, meaning they kind of pass in front of the same part of the star. If we see a signature for planet B, which we did, helium, we detected helium, and planet C passed in front just before, but we didn't see any signature, that is helping us rule out that false positive and say, okay, well, if we saw a signature for B but not C, it's probably not due to the star, or else we should have seen that signature for C as well.
What telescope did you use to look at these worlds?
Yeah, so we use the Magellan Clay Telescope. This is a 6.5 meter telescope, really big, in the Atacama Desert in Chile. And we use the wine red spectrograph, which was developed by a Japanese team and moved there recently, which is a really great high resolution spectrograph that's sensitive to near infrared light, where we could probe this helium.
So this was a special case. You got to see two planets for the price of one, but you observed this exoplanet on more than one occasion, right?
Yeah. So we made the discovery in 2024. That's when we got the detection. And then we went back a year later to reproduce the finding and repeat the experiment. And we did not see any helium absorption, which was really surprising. And so this caused me to go back and really just tear that data apart in 2024 and say, okay, did I miss something? Could there be another false positive sort of lurking here? Did I make an error? Me and my teammates, we spent months really thoroughly investigating that data, and even sent it off to another colleague who did a blind reanalysis with a fully independent pipeline and found the same results. And fortunately, because of some of the idiosyncrasies of the observation, we were able to rule out a lot of typical false positives. So these are basically things the star can do that make it look like there's helium absorption happening. And so we're really confident, we're extra confident in that original detection now, which begs the question, what happened in 2025? Why did we not see anything? And this is really fascinating. It's a really open question. I mean, it's really rare to see like a planet's atmosphere change like that on like human-like timescales of like 1 year. I mean, that's kind of awesome. We typically think of atmospheres evolving on like millions to hundreds of millions to billions of year timescales.
Absolutely. I mean, I'm curious, like what could cause that kind of variability?
So it's an open question. And one thing I've learned recently after seeing that and talking to a lot of other experts in the field who have done a lot of these helium observations and, reading more papers, interestingly, it almost seems to be the rule and not the exception to have variability. Oftentimes when you measure this specific helium, the metastable helium triplet, that's an excited state of helium, you measure it once and then you go back even a couple months later or a year later or more, you typically see a different value than what you got the first time. And it can be very different. And in other cases, there have also been just straight up detections and non-detections. And these are for hot Jupiters, planets that, are mostly composed of hydrogen and helium and are so much hotter than LHS 1140b. And you have copious amounts of helium just streaming off of the planet, hundreds to thousands to 10,000s of times faster than what we saw for LHS 1140b. And even in those cases, you see this kind of variability. So that, made me think, okay, this is not, maybe this isn't so wacky. And some of the physical explanations that have been given, mainly revolving around the star. So for one thing, I think the first obvious place to start is, okay, could the X-ray and ultraviolet radiation from the star be changing? And that's the question, because it's the X-ray and ultraviolet, or XUV radiation, that tends to heat planetary atmospheres and drive them off into space and cause escape. And we know from our sun that stars can have magnetic activity cycles, right? Where, for our sun, it's every 11 years, it follows this really nice sine wave, and the X-ray, ultraviolet, visible flux all changes together pretty substantially. And so, maybe that's happening. Maybe the XUV flux of the star is varying, and that's actually causing the helium escape to vary in time. We also know the three-dimensional shape of the escaping helium is really important. This is a notoriously difficult thing to model, and it's still very poorly understood, because we're talking about like fluid dynamics here, which is, famously difficult in physics. But yeah, we're talking about fluid outflow of gas here, and it can, there can be things called shear instabilities, which can kind of change the shape and perhaps lead to non-detections. Also, the last thing to consider is the fact that, again, this is not just your normal, neutral, regular helium, like ground state helium atom. These are excited helium atoms that come from when the helium atom is ionized, so it loses an electron, and then it gets that electron back, but the electron's in a higher energy state. And that can be stable for a long time, which is what we observe. And that's a very specific type of helium, and it's only existing very far away from the star in what we call the exosphere. And it's really sensitive to the stellar environment. It's really sensitive to the exact amount of ultraviolet flux at different wavelengths coming from the star. It's also sensitive to like stellar wind and all these things. So, it's possible that there was helium escaping in 2025, and it's just that not enough of this metastable helium was sort of populated for us to see it. So these are some of the big ideas. Time will tell. We're gonna keep observing it. I have another program right now where I'm observing the X-ray and ultraviolet flux of the star over time to see if we can see any variability.
Yeah, I mean, it's one thing, the stellar cycle going on, but this is also going around an M dwarf star, which are classically feisty. Is it very volatile, or is it a more chill star at this point?
It's pretty chill. It's chilling. Yeah, it is an M dwarf, and these are notoriously feisty, especially this class of M dwarf. This is a mid-M dwarf that is expected to be fully convective, meaning its structure is very, very different than the sun's, and that gives rise to really, frankly, poorly understood magnetic activity that can drive high energy emission of X-rays and ultraviolet, and typically results in lots of flaring and potentially coronal mass ejections. But what's really kind of a happy coincidence about this star is that it's very, very quiet relative to typical M stars that exhibit all that activity. It's over 3 billion years old. So, it's had time to kind of chill out and mature, as stars do as they age. I guess kind of like people. And yeah, it's actually never been observed to flare in all of the years we've been observing it, which is pretty remarkable. And it emits a very low amount of X-ray and ultraviolet flux compared to stars of that type. So this planet is actually receiving somewhere between 3 to 10 times the amount of X-ray radiation as we do on Earth from our sun. And that is actually remarkably low. That might sound like a lot to people, like, oh no, I'm getting 3 to 10 times as much, X-ray radiation. I mean, that's kind of nothing. You look at Proxima Centauri b, this is the closest rocky planet to the Earth. It's kind of in our backyard, and it's receiving something like 200 to 300 times the X-ray radiation that we are, because Proxima Cen is such a active star. So yeah, it's a really, really quiet star, which makes the planet easy to observe and is really good for habitability.
Oh, yeah. And I mean, that bodes well, because there might be all kinds of things going on with this world. It could someday be looked at even closer as a candidate in the search for life. So knowing that the star is pretty chill is an important question. We'll be right back with the rest of my interview with Collin Cherubim after this short break.
Hi, I'm Kirby Runyon, planetary geologist at the Planetary Science Institute and founder of Planetary Experience Consulting. Think of your favorite photograph from the moon or Mars. Have you ever wanted to read the stories recorded in those rocks? You can learn how. This October, I'm co-leading a 3-day expedition to some of New Mexico's finest planetary geology analog sites, and I'd love for you to join me. From October 15th through 19th, we'll explore tube-fed lava flows at Carrizozo, soak in the volcanic desolation of Kilbourne Hole volcanic crater, and stand at sunset over the sublime White Sands National Park. These are some of the same landscapes where Apollo and Artemis astronauts have trained. We'll also visit Spaceport America, the New Mexico Museum of Space History, and the Las Cruces Challenger Learning Center. Space is limited to just 20 people, and for every person who registers, the Planetary Society will receive a donation. Head to planetary.org/travel to learn more and save your spot. I hope to see you there.
You keep bringing up in this conversation this idea of helium streaming off of these kinds of worlds, which is evoking this kind of almost like comet-like idea, like the atmosphere is literally being stripped off in a way that you can observe and maybe model its shape. Is that the case with this world? Like, do you know that there's actually this material streaming off, or are you just seeing it in the atmosphere?
We do have some evidence to suggest there is some sort of three-dimensional shape that might be kind of comet-like in our 2024 data. So in the 2024 data, you can see a little bit of helium absorption before the planet even gets to the star, and a little bit after the planet is sort of out of the way of the star, or we call that egress, or post-transit. So just after it sort of finishes eclipsing its star. And this is suggesting that there's like helium in front and behind of the planet, right? And that's consistent with previous observations, and it's consistent with theoretical models too, which is really nice when those things kind of line up. And yeah, what you expect is you kind of get this like leading arm, so to speak, of material, of helium in this case, sort of streaming towards the star in front of the planet, and this trailing tail, so to speak, behind the planet that is oftentimes kind of being blown away. And you can kind of see that in the red shift and the blue shift of those tails kind of moving towards or away from the observer. We can't do like super detailed modeling based on our data because it's just not really detailed enough. But again, like in 2025, we didn't really see that. So we don't know if that's a sort of stable feature where you can go, if you were able to theoretically go to this planet and look at it, I don't know if you would see a stable, steady stream with some kind of definable shape. But I should also mention that the helium escape from this planet compared to previous observations is on the very, very low end. So it is sort of hydrodynamic, we expect, probably, where it's like enough gas is escaping where it's literally like flowing off the planet. So it's a lot, but it's, orders of magnitude less than what we see for giant planets. So what the shape looks like, we don't fully know. And, I'll also point out that Earth itself actually has a really big hydrogen corona, which basically means that hydrogen gas is enveloping planet Earth, so much so that corona, that gas bubble, extends beyond the moon. It's really big. And so if you were to look at Earth transit the sun with a sensitive enough telescope, you might see this massive cloud of hydrogen surrounding the Earth. And you might even see the same kind of thing where it starts before the planet transits and it ends way after the planet transits. And you can also see helium in Earth's corona too, but it's escaping at a much, much, much lower rate.
That's really cool. I hadn't even thought about this streaming hydrogen off of the Earth. But I mean, it makes sense. Like we're a water world, right? And I think this brings up something really interesting about LHS 1140b that was in this paper, is this idea of the ratio between hydrogen and helium and what that's telling you about this world. What did you find?
This is actually, I think, really remarkable, and something I'll just spill the beans. I'm actually planning to hopefully write a paper about this, because I think this finding in and of itself could be really helpful for the community and kind of a big deal. But we were able to place some observational constraints, meaning we could basically estimate the ratio of hydrogen to helium in this escaping outflow just based on the spectral line. So the observation, we have the spectrum. By fitting that spectrum with different models that have different hydrogen and helium ratios, we could get a pretty good idea of what that value is. And we found that it was very, very low. So the hydrogen to helium ratio was something like 0.1%, meaning the vast majority of the outflow appeared to be helium, and it appeared to be very hydrogen poor, which has never been done before for a couple reasons. One, I don't really think we've observed or identified any kind of like helium world like this, where it's, the majority of the outflow is helium. But two, more importantly, I think that type of measurement doesn't typically allow you to measure the hydrogen to helium ratio. And the reason is because when you have so much hydrogen and helium escaping from a planet, like for a sort of sub-Neptune or a giant planet like a hot Jupiter, the sort of solution space is just too big. You can just tweak too many knobs to kind of reproduce the feature that you're seeing. And that allows for lots of potential hydrogen helium ratios to totally explain your data, like totally fairly. What was really interesting about this discovery is that there were not a lot of solutions that could explain this discovery. And I think the reason is basically it's a bit nuanced, but it's because this planet is so cold. It's so far from its star. It's receiving very little of this X-ray and ultraviolet radiation that powers this escape. And therefore, the models tell us if you have any amount of hydrogen in the outflow, that basically shields your helium from this ultraviolet flux that is in already very low levels, and it prevents that helium from getting ionized and becoming this metastable helium that we see. So essentially what I'm saying is the hydrogen would act as a shield, and it would block the helium from this sort of UV starved environment. And that's really cool, because I think this might be a new method for actually observationally measuring this hydrogen to helium ratio for planets like this.
What does that tell us about this world? Like, can we hypothesize about what might be going on the surface because of this hydrogen to helium ratio? Or are we just assuming that it's not there?
Yeah, we can totally tell some things about the surface based on that. I will say we're not, super confident about that hydrogen to helium ratio. The models are a bit simple at the moment, and we continue to improve them. But it is totally consistent with my prediction that it should be helium dominated. So it's not totally surprising. And when you have the theoretical prediction and you have the observation to support it, it's starting to paint a pretty compelling picture. So assuming that it is truly helium dominated, that totally tells us more about what's going on the surface, because that means the atmosphere is likely to be hydrogen depleted, right? Because hydrogen escapes even more easily than helium. So if you're not seeing it escaping with helium, then there must be really small amounts of hydrogen. And just as my model predicted, that means the atmosphere, especially at lower altitudes, should be rich in more oxygen-rich and oxidizing species. So the most common would be like CO2, right? Carbon dioxide. We're also predicting some carbon monoxide, CO, and even molecular oxygen, O2, like what we breathe. And just to be clear, that would not be from life. That's just from natural processes, and also water. And this is consistent with this picture of mass fractionation that we talked about earlier, where lighter species escape more readily, and you kind of distill the atmosphere and concentrate these heavier, more oxidizing species. And because we expect a really strong, what we call a cold trap on the planet, meaning, like, let's take water, for instance. On the Earth, when water goes up into the atmosphere, it gets colder and colder. And eventually it condenses out. It becomes liquid or ice in clouds, and then it rains or snows back down. And fortunately for us, that traps water on the planet and prevents it from escaping. And we think that would be definitely happening on LHS 1140b because it's a very cold planet, and we think it has an atmosphere now. So that would trap things like water, and it would also mean that volatiles, gases are probably not there, like ammonia or methane, because if these things were there, they actually would not be cold trapped, and we would see that hydrogen higher up in the atmosphere. So this is all pointing to a picture of a sort of oxidized lower atmosphere with lots of water, probably CO2, and maybe even a little bit of O2 kicking around.
Oh man, that bodes so well. It's like we're literally seeing this world distill its atmosphere. It's so cool.
Pretty cool to see in real time, especially because we think this has happened. Similar processes have happened in the solar system, which is what my theory is founded on. It's what folks have done with solar system objects. So it's really cool to actually see this like potentially happening in real time.
What did it feel like the moment that you were looking at the data and realized what you captured here?
I wish I could tell you it was like a movie and, it was like Call the President or whatever, but it was a lot more kind of tame, I think, for good reason. So I was in Pasadena. I was visiting my colleague, Shreyas Visapragada, who is a researcher at Carnegie Science in Pasadena. And he played a huge role in this and really helped to actually teach me a lot of these techniques that I hadn't done before to analyze these data. And I went to go visit him, and this was actually right when the fires were happening, and I think Altadena, and so a lot of people were kind of displaced, and the hotels were really filled up, and Shreyas just happened to be sick when I visited, and so he said, we should really just meet on Zoom. So I went all the way to Pasadena, and it's on fire, and I'm in a hotel, and Shreyas can't even meet with me, so I was on Zoom in a hotel room when we were finishing up this data analysis together. And mind you, this was like 4 or 5 months at least after I collected the data, and it just sat on my computer because I was busy writing another paper. And I was like, it can wait. There's probably nothing there anyway. And then, so, I remember we got to the kind of final stage of the main part of the data analysis. And I remember hitting enter on my keyboard, and, this figure pops up where it shows us the spectrum. And we both just kind of go, whoa, and just kind of pause for a second, and we're quiet. We're like, that looks a lot like a helium signature. And, I started to get really excited, and I was like, wait, man, hey man, if this is true, like this has really big implications. And I think it was Shreyas who was kind of like, okay, let's take a beat. Let's calm down for a second. Let's just think about, we need to vet this. Like this could be stellar contamination. It could be a false positive. We don't know if this is real. Okay. We gotta do a lot of groundwork. And so that kind of sobered me and kind of brought me down to earth. And I was like, oh man, okay. Like, I guess this is just science, huh? It's really really careful, tedious process that takes a long time. And so it was only like, it was a slow process over many, many, many months that followed that we became gradually over time more and more confident, rather than it being a real, aha moment where it was like, we're done here. We just figured this out. This is the result. You really have to be careful with these things. And as Carl Sagan said, to bring it full circle, extraordinary claims require extraordinary evidence. So
yeah, you have to go through the whole process, but now it's official. Like we have a rocky world in the habitable zone of a star with an atmosphere. I mean, this is, it's not surprising. We knew they were going to be out there, but to actually have crossed this threshold and knowing how many exoplanets we have out there and what's coming up in the future of exploring these worlds, like this is the beginning of a whole new chapter.
Totally. Yeah, it's absolutely riveting. It's really exciting. I think it's a true milestone, and I really hope it's the first of many to come. And that's kind of where my mind is next. It's like, what's next? Is it going to be an oddball and this gem that is our only laboratory to kind of study astrobiology, or will there be many more to come?
Well, what are the next steps then on this?
It kind of almost goes without saying, lots of people are training their telescopes on this target for the time being and really studying this. I mean, I count at least 4 or 5, potentially more, different observatories that are going to be observing it for its next upcoming transit, observable from the ground. So, we're just going to really keep observing it. I think the next step people want to know is, can we observe molecules deeper in the atmosphere, right? I only observed helium. That's an atom in the exosphere. Yeah, we want to know the chemistry of the planet, of the atmosphere, and could it truly be habitable? And so right now, unfortunately, like with the James Webb Space Telescope and the Hubble Space Telescope, that is just out of reach. Those spectra have not shown any statistically significant signatures. And I think it's likely that if we keep observing with those instruments, and when you combine that data, you boost your signal to noise. So that means the noise becomes less prohibitive to actually seeing these molecular features in the spectra. I think something will probably start to emerge. Water, CO2 are probably the most likely that have strong features to be able to see in the infrared where these telescopes are looking. So I'm hoping that's the case. We also really have to resolve what's going on with this time variability with the helium. But yeah, I'm personally actually thinking more big picture. While I do have plans to keep observing the planet and the star to see if its activity is changing, I'm really actually more excited about continuing to test my predictions that led to this discovery. This was really just the first test of my kind of helium world predictions that come from my model that I call isofate. And I want to continue developing my model and improving it and just testing the predictions. And I have a handful of targets that I already have in mind that are similar to LHS 1140b, and I plan to observe those and keep testing those predictions.
This is just such a cool discovery, and all these things coming together leaves us with this question mark in our heads. Are we actually seeing a rocky world potentially with water on the surface that has this thick helium atmosphere? I mean, it fills my imagination. I wish I could just go there and see what it looks like.
Oh, me too, truly. Unfortunately, it's 49 light years away, and that's probably beyond our reach, you and I, but who knows, maybe in the future, someone will figure something out.
Maybe. Well, seriously, I'm so excited that we can share this story and this next major step in our search and understanding of exoplanets. And I wish you so much luck in your next chapter. Now that you've got your PhD, you're off doing your fellowships, and you've got so much more science left to do. I cannot wait to see what you do next.
Oh, thanks so much, Sarah. It was really great chatting with you. This was super fun.
It's funny because LHS 1140b has inadvertently become something of a recurring character on this show, even though I'm sure almost no one would notice. Back in 2023, I spoke with Dr. Luzendra Oja from Rutgers University. We talked about subsurface oceans on exoplanets orbiting red dwarf stars. He used LHS 1140b as a case study, walking us through how its powerful surface gravity could crush ice into exotic high-pressure phases and potentially sustain liquid water deep beneath that surface through the planet's own interior heat. Of course, to reiterate, we don't know that it has an ocean, but at that point, the question was whether or not that world could be hiding an ocean under hundreds of kilometers of ice. We still don't know the answer. Then in 2025, planetary geochemist Dr. Chris Glein came on the show to talk about a different exoplanet, a sub-Neptune called TOI 270d. Near the end of that conversation, he brought up LHS 1140b. By then, the James Webb Space Telescope had observed it and gotten back a flat, mostly featureless spectrum, which actually hinted at something exciting. Unlike the puffy hydrogen-dominated atmospheres that we see on sub-Neptunes, that flat spectrum suggested that if LHS 1140b had an atmosphere, it might be a denser, more Earth-like atmosphere. He called it a possible supersized ocean world. And now, with the discovery by Collin Cherubim and his team, we have the first direct evidence that that world actually does have an atmosphere, and a physical mechanism explaining how that atmosphere is transforming itself over time. In just 3 years, our understanding of this world has changed dramatically, and I'm sure that it's going to continue changing as we explore. But for now, we're just going to have to be patient. Let's check in with our chief scientist here at the Planetary Society, Dr. Bruce Betts, for What's Up. Hey, Bruce.
Hello, Sarah.
Hello. Man, we finally did it. We found an atmosphere on a rocky exoplanet in the habitable zone. I feel like that's a moment.
When you say we, you're referring to
humanity.
Humanity. We keep making moments in the exoplanet world. We keep doing that. It's cool. We keep getting a little bit more, a little bit different. A lot of exoplanets out there, it turns out, and they're variable. But for some reason, they're really hard to see.
For some reason. I mean, even in the case of hot Jupiters, as we discussed in a recent episode, it's still really complicated to learn more about these worlds at this distance. But I think this situation with Collin and their team finding this is just a really great example of this idea of like mentorship within the space realm. Like so many of these situations happen because someone discovered something, taught it to the next generation, and spread it on whatever. But in this case, Collin was actually the grad student of David Charbonneau, who was one of the people who discovered the first atmosphere on an exoplanet. And now 25 years later, his student is helping to discover this whole new thing. I love that. So I wanted to ask you a little bit about that first exoplanet that they detected an atmosphere on and what they actually found there.
That was, of course, HD 209458b.
Oh yeah, I'll remember that forever.
Sometimes unofficially known as Osiris, but officially the other, which is basically the star catalog designation and what it was found, and then throw B on it. For the A is always, you never see A because it refers to the star, and B is the first planet they find in that system. And it is a hot Jupiter. So it's a big gas giant, not quite as big as Jupiter, 150 light years away in Pegasus, and was one of the first exoplanets ever to seen transiting its star, going in front of its star. And in fact, it was using Hubble spectrograph that they were able to look at those transits and determine that it had, they found a sodium, for those who play in spectroscopic land, a sodium doublet that they could see in that planet's atmosphere. So from that, they deduced, hey, there's an atmosphere there. But this was a very different beast than what was just found. Hot Jupiter, meaning big and near its star. So significantly, like 8 times closer or something to its star than Mercury is to the sun. So a very different beast, and it was seen to be losing its atmosphere and other observations. So yeah, kind of cool, the continuation of knowledge gathering by the generations.
Between JWST and all of these other new telescopes coming online, and someday, Habitable Worlds Observatory, there's just so much that we're about to learn about these worlds. Like right now, we're having a great time because we found an exoplanet on a rocky world in a habitable zone, but soon that's just going to be a thing. We'll find a bunch of them.
Yeah, that's kind of how it works. The better we get at it, but it's still, I mean, the technology used to do this is still just amazing. I mean, the things they're detecting, the differences, the accuracy of their data gathering is really unbelievable. That they have to do, especially as you get farther from the star and smaller planets. Whether you're doing transit or whether you're doing another method. Anyway, back to you, Sarah.
I just wonder if anybody else, there are these moments where I'm just staring up at the night sky and it just kind of hits me. Like every single one of those stars probably has a world around it. And there's just so much out there that we don't know. And I wonder what portion of humanity has that same reaction when they look at the night sky. How many people really fathom how much is out there just waiting to be discovered? It might just be me. And I'm sure that's a similar situation for so many people in the space community. But I wish everyone felt that when they looked at the night sky.
I do too. And that's why we do what we do. And especially why you do what you do and get people excited and get psyched. It's pretty neat. Now, I don't ever hope to fathom how much there is known now, much less what will be known. But it's kind of overwhelming or exciting, depending on your view of the universe. Sure. That on average, every one of those stars has a planet. And some of them are going to be Earth-like, and some of them are going to be hot Jupiters and weird things we didn't know about till we started looking, when we only had our solar system as a model. And so it's knowledge, and it is cool.
It is.
You know what else is cool? Random space. rewind. The altitude of geostationary satellites, so the ones like your dish networks point at that move over the same part of the Earth. So that's geostationary satellites are over the equator, following the path, the time frame of the Earth's rotation. But here we go to the fact, which is the altitude of geostationary satellites is about 100 times higher than the altitude of the International Space Station.
Oh.
They're out there.
Far out, man. But it's really cool that we figured out at all how to have geostationary satellites.
Yeah, well, those started kicking up, I think, in science fiction back in at least the 50s, if not before that. The idea, at least in some of Arthur C. Clarke's work, but others as well. No, it is cool.
Put a little funding in science and who knows what we could do. I don't know. I'm just really excited about this result and knowing that we finally crossed this threshold. And I'm really excited for the whole next era of investigating exoplanets. So thanks for listening to my joy, Bruce.
I've enjoyed your joy, and everybody go out there, look up the night sky, and think about your favorite threshold in your abode. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review and a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email, planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members all around the world. You can join us as we support the exploration of worlds beyond Earth at planetary.org/join. Mark Hilverda and Ray Paletta are our associate producers. Casey Dreyer is the host of our monthly Space Policy Edition, the next episode of which comes out on Friday. And Matt Kaplan hosts our monthly Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. My name is Sarah Al-Ahmed, the host and producer of Planetary Radio. And until next week, Ad Astra.